A wafer boat has to travel deep into a furnace tube supported from one end only. No prop under the far tip, nothing to lean on. And it must arrive dead level so every wafer sees the same heat and the same gas. A silicon carbide cantilever paddle is the single arm that carries that boat the full length of the tube and holds it steady. Tapered so it reaches far, hollow so it stays light, and stiff enough that the tip barely drops. Reaction-bonded silicon carbide gives the blade an elastic modulus above 380 gigapascals, so under the weight of a fully loaded boat the arm resists bending far more than quartz or a metal alloy would. That stiffness is what keeps a long reach from turning into a sag. Its body holds under 1% closed porosity and carries no free metallic contaminants, so it stays inert in the oxygen, nitrogen, and argon of a furnace and releases no particles onto the wafers. The clean surface is as important as the strength. A paddle that sheds contamination fails the process even if it never bends. With a thermal expansion near 4 parts per million per Kelvin and stable strength, through repeated cycles above 1200 degrees, the paddle keeps its shape and its straightness where the process runs hottest, the same geometry after hundreds of load cycles as on the first. A cantilever loaded at its free end droops by an amount that follows a simple rule. Deflection rises with the load and with the length cubed, and it falls as the material gets stiffer and the cross-section gets deeper. That cube on length is the trap, double the reach and the tip sags roughly 8 times as much. 2 levers fight that cube. The first is stiffness. Silicon carbide above 380 gigapascals resists bending far more than quartz near 72. The second is the shape. Pushing material away from the center, as the hollow square root does, raises the section's second moment of area, so the same mass of ceramic resists bending much harder than a solid rod of it would. Put high stiffness and a deep hollow section together and the numbers land where the process needs them. The tip of a fully loaded paddle drops less than 0.2 of a millimeter over its full span, which keeps every wafer slot level and every wafer in the same thermal and gas environment. The paddle's length is set by the furnace tube it must reach through, from a few hundred millimeters for compact reactors out to several meters for the longest horizontal diffusion tubes. The fork and cradle at the tip are shaped to the boat it carries, which in turn suits wafers from around 100 up to 210 millimeters. From that starting point the whole profile is drawn to the line. The root cross-section and the taper are sized to hold deflection within tolerance at the required reach. The fork is matched to the boat, and the mounting end is cut to the loader, so a longer tube simply calls for a deeper section rather than a paddle that droops. In a photovoltaic diffusion line, the paddle carries a boat of solar wafers straight into a horizontal furnace tube held between roughly 1000 and 1300 degrees, where phosphorus diffuses into the silicon to form the cell junction. Because the arm holds the boat level from that single supported end, the wafers at the tip sit at the same height as the wafers at the root, so the gas reaches every slot evenly and the diffusion comes out uniform across the load. The high purity means the arm adds no metallic contamination to the wafers during the soak, and the stiffness means the boat neither dips nor drifts as it travels the length of the tube. Drawn back out after the cycle, the blade comes away as straight as it went in. No permanent bow, no clouded surface, no lost tolerance. And turns around for the next load. Hundreds of cycles on, the tip still lands within the same fraction of a millimeter it did at the start. Unbendingly, one slender arm reaching the full length of the tube is what keeps every wafer in the batch on the same plane, the quiet backbone of the diffusion step.